At D-Wave, we have charted a course of aggressively pushing the frontier of quantum annealing processors and performance, and we continue to do this with our new quantum computer, the D-Wave 2X, the most advanced quantum computer in the world. Back in 2010, we released the D-Wave 1, which included a 128-qubit quantum annealing processor, which was realized in a truly scalable architecture. In 2013, we shipped the first D-Wave 2, which included a 512-qubit quantum annealing processor, which outperformed general-purpose optimization solvers and achieved performance on par with highly optimized heuristic solvers. Now in 2015, we have announced the D-Wave 2X, including the quantum annealing processor with over 1,000 qubits, as well as many technology improvements aimed at boosting quantum annealing performance. The new system runs at a colder operating temperature below 15 millikelvin, which helps the quantum annealing algorithm stay in low energy states and improves solution accuracy. Other improvements include increased control circuitry precision and a 50% reduction in qubit noise, which also combine to improve performance. With over 128,000 Josephson tunnel junctions, the new processors are believed to be the most complex superconductor integrated circuits ever successfully used in production systems. Our latest benchmarks on the D-Wave 2X show competitive performance against the best-known highly tuned software solvers running on CPUs. On benchmarking problems, the D-Wave 2X finds near-optimal solutions up to 600 times faster than classical solvers if you compare the quantum processing time to the CPU time. The D-Wave 2X was recently installed at the Quantum Artificial Intelligence Lab at the NASA Ames Research Center in California. This lab supports research into machine learning and optimization by Google, NASA, and USRA member universities. Our new agreement enables Google and its partners to keep their D-Wave system at the state-of-the-art for up to 7 years, with new generations of D-Wave systems being installed at NASA Ames as they become available. The D-Wave 2X is the culmination of years of hard work, and we can't wait to see how this changes the landscape of computing.
I'm Jeremy Hilton. I'm the Vice President of Processor Development at D-Wave Systems. I'm responsible for the processor development group, which involves the design, test, and development and release of the quantum processor that D-Wave makes, which is the underpinning of the quantum computers that we build. Each of these black systems is a quantum computer. Inside that system is a thumbnail-sized quantum processor. In order to operate and develop quantum processors, we require a fairly extreme operating environment, which includes ultra-low temperatures and an ultra-low magnetic environment. And to achieve those, we need a fairly large and sophisticated system. The main room behind us houses the quantum processor, and the data racks in the front hold the quantum server, where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in. If you look inside the data racks, you'll see that they don't contain what you would normally expect. So here we have some scroll pumps, which are mechanical parts associated with pulling vacuum on the fridge inside the room behind. So this is obviously highly unusual for a data rack, but has been integrated so that it wouldn't look out of place in a data center. And in fact, the requirements for running the system are consistent with all the services that would be available in a data center, which would include chilled water and power predominantly. In this rack is the quantum server, which allows users from anywhere in the world to interact with the processor itself. This server is receiving information from users, converting that into the machine language of the processor, and sending that machine language into the room behind, where high-precision analog electronics will convert those signals into electrical pulses, which are sent through cables into the refrigerator and down through the cooling system to the ultra-low temperature of the processor. It executes its problem, and then data from the processor is returned to the server and returned to the user. And the system is very flexible, and that users can be programming in whatever language they're comfortable with, and interacting with it either with this system in their data center or even here in D-Wave's lab. The quantum bits in our processor store information in the form of little magnetic fields. The 0 and 1 correspond to a little magnetic spin. The controls over the qubits are all in the form of magnetic fields. So the quantum processor is very sensitive to magnetic noise and the magnetic environment that it sits in. In order to keep that magnetic environment really low, as well as support the ultra-low temperature that it's operating at, this system behind me has about 16 layers of shielding between where I'm standing and where the chip sits at the center. These black panels are really for aesthetic purposes, and they integrate these data racks with a shielded room, which is the first of those layers of shielding, and is filtering out RF signals. So if you were to stand inside the room and close the door, your cell phone would stop receiving a signal. The fridge itself has a combination of radiation shields as well as magnetic shields, which help support the ultra-low temperature operating environment and achieve the ultra-low magnetic field. Inside the room, we have to keep electromagnetic noise very low. So even things like power outlets aren't allowed, because power can be quite noisy without extensive filtering. So inside the room, we have the cooling system, and these are radiation shields. So this is the next layer of shielding inside the room. The chip itself, the quantum processor, is sitting at the bottom of this array of shields. And this is, again, the first of several more layers. Inside these shields is vacuum, which is the insulation of the cooling system. When we want to swap the processor or conduct maintenance on the fridge, we warm the system up, we remove these shields, and then the processor is accessible, as well as all of the internals of the refrigerator.
My name is Murray Tom. I'm the Director of Professional Services at D-Wave. I talk with our customers and partners about what quantum computers are, what kind of problems that they solve, and work with them to develop software that uses quantum computers. We're standing inside a quantum computer. And you may know that the quantum world is delicate. It's easily disturbed. So there are many layers of shielding in this system, which we've removed in order to look at the internals here. A traditional supercomputer may have many thousands of processors in it, but in this quantum computer, there's only one chip located right down here. When you send an instruction to the quantum computer, a delicate quantum calculation is taking place on that chip to produce your solutions. The system we're looking at here is an ultra-low temperature cryogenic fridge. Because it works at such low temperature, we use the Kelvin scale to measure how cold it's getting. In the Kelvin scale, a warm room is like 300 Kelvin, and 0 Kelvin is the lowest temperature that can be reached. Physicists refer to it as absolute zero. There's two levels of cooling in this system. The top one is a pulse tube refrigerator, which takes us from 300 Kelvin to 50 Kelvin, and then down to 3 Kelvin. This is roughly the temperature of interstellar space. And then a second refrigerator, a dilution refrigerator, takes us in this plate from 0.7 Kelvin, 0.1 Kelvin, and then down to 0.01 Kelvin. When the system is operating, this plate and everything mounted below it is 10,000ths of a degree above absolute zero, which is more than 100 times colder than interstellar space mounted here. And this whole system is designed to sustain those low temperatures in a continuous cycle. When you send an instruction to a quantum computer, the signals pass down these wires along the sides of the refrigerator. And at this point, there's a break in the wires where all the signals become superconducting. Superconductivity is this amazing effect where you can send electrical signals without any resistance whatsoever. So the electrons aren't even interacting with the atoms in the wires around them. That's great because it means that this portion of the system has no energy dissipation, it produces no heat. But it also means that we can't rely on the wires to cool the electrical signals and eliminate their noise. So we have a custom filter bank mounted here which cools those electrons. An important aspect of the superconductivity is that these signals and the quantum processor unit consume virtually no power, whereas the supporting systems around it consume about 15.5 kilowatts. And this remains the same regardless of which processors are installed at the bottom. If you were to take a fully populated server rack out of a traditional supercomputer, it might consume 10 times that much power. So for our first customer, Lockheed Martin, when they upgraded from their first chip to the D-Wave 2, they saw a relative performance improvement on the order of 10,000 times, but the power consumption for the system was the same.
Hi, I'm Mark Johnson. I'm a scientist at D-Wave Systems, and I work with a team of other scientists and engineers developing the superconducting integrated circuit chip that's at the core of our quantum annealing processor. We have our chips fabricated on 8-inch silicon wafers, and when we receive them back from the foundry, they look like this. Here, if you look closely, you'll be able to see a repeated array of squares that are multiple copies of our integrated circuit chips. That integrated circuit chip is really just a series of metal layers, predominantly, which you can see in cutaway here. The process that goes into fabricating this integrated circuit chip is actually not that different from that which goes into making the chip that drives your cell phone or your laptop. One of the principal differences, though, is that these metal layers are actually made up predominantly of niobium, and niobium is chosen because it's a superconductor. So the thing about a superconductor is that when you cool it down below a certain temperature, all of the electrons really collapse into the same quantum state. In a sense, they cooperate with each other in the way that electrons in a normal metal don't. Now, ordinarily, quantum mechanics only exhibits on the scale of atoms, electrons, or photons. Superconductors are unique in this way in that you can see quantum behavior on a much larger scale. And it's these properties, these quantum mechanical properties, that enable us to use these materials to make our quantum processor. So this is a blueprint of one of our processors. The design and construction of one of these is not really that different from that of a conventional processor, but a really important difference is that on a conventional processor, the ones and zeros are encoded as voltages and currents on that chip. In this processor, that information is actually encoded in small magnetic fields called single flux quanta, or quanta of magnetic flux. When we're programming the processor, we load hundreds of thousands of these flux quanta into the chip, into various circuits. Then the processor undergoes this algorithm, quantum annealing, which is how it solves the problem that we've posed to it. At the end of that, the answer is in the form also of magnetic flux quanta, which are then pulled out of the processor to the four corners and then up into the room temperature electronics and onto a conventional computer. So the basic computational element in a quantum processor is a qubit. Now, a qubit is a lot like a bit in the sense that it can encode a state as 0 or 1, but it's a quantum bit, Q for quantum bit, and it has the additional property that can be in a superposition of 0 and 1 at the same time. So this chip is made up of repeating tiles or unit cells, and each one of them is made up of 8 qubits. Now, if you take one of these unit cells, well, we can blow it up and get a better view of it here. So our qubits are actually superconducting wire loops that are interrupted with a circuit element called a Josephson junction. And we make our qubits long and thin. You can see that there are 4 of them running vertically here, and another 4 running horizontally here. Wherever these qubits cross or intersect with each other, we put a tunable coupling element that can be used to allow the qubits to influence each other in a programmable way. A qubit is engineered so that there are 2 stable states corresponding to circulating current going clockwise or counterclockwise. And associated with those 2 stable states are magnetic field either coming out of the surface or into the surface. And they correspond to the 0 and the 1 state respectively for the qubit. Of course, a qubit can be in a superposition of 0 and 1, and so in this case that means that these qubits can be in a superposition of those 2 circulating current states going clockwise and counterclockwise at the same time. So the idea that a macroscopic object like a wire loop could really be in a superposition state of circulating current going clockwise and counterclockwise is counterintuitive. It's quite odd. But this is the sort of thing that happens in quantum physics on the microscopic scale. And this is exactly the sort of phenomena that we're harnessing to make our quantum annealing processor.
I see quantum computation as being a tool that can solve problems that you could never otherwise solve.
Doing genomic analysis to help find better drugs.
Debugging large, complex systems.
To looking for bad guys in large amounts of data.
Space exploration.
Trying to optimize waterworks.
Building artificial intelligences that can help us solve very difficult, complex problems.
Building a quantum computer is a historic thing. And it's really like venturing into uncharted territory. There's no precedent here.
Quantum computing literally taps into our most fundamental understanding of the laws of nature.
In nature, there's this almost spooky phenomenon called quantum mechanics, where a thing can be in two states at the same time. And so the D-Wave quantum computer uses that strange property. What the quantum computer actually does is it's able to compare many possible solutions at once. So if you imagine a regular computer, if it was searching for a solution, it would have to go through every possible solution one by one, see if that's a good fit. What the quantum computer does is it kind of lays all the solutions down and compares them all at the same time so it can pick out the best one.
The D-Wave system is built to solve discrete optimization problems. These are types of problems where you've got a load of constraints and you're trying to find the optimal answer to your set of constraints. Say you've had some kind of natural disaster and you've got a load of people who need help, and you've only got a limited amount of resources to go help them. So you've got a few lifeboats and a few helicopters. What you need to do is work out what order to send things and where to send things to save the most amount of people as possible. This is a hugely complex problem because there's so many possible different combinations of sending them in different orders. So this is the kind of thing that finding a fast answer is really important.
The D-Wave computer has two, what I would say, really sort of exotic operating conditions. We put our quantum processor into something called the dilution refrigerator, which cools it down to 10 millikelvin, which is about 100 times colder than interstellar space, and essentially is the coldest place in the universe. We have to also create an extremely low magnetic environment for the processor to sit in. That's about 50,000 times less than the ambient Earth's magnetic field. And so there are these two extreme conditions that the processor has to be running.
In this company, you know, a few dozen people in 10 years have managed to make a technology that can match and beat the existing normal computer technology that's been developed, you know, all around the world for 60 years.
We have an incredible future ahead of us. First and foremost, we're just going to increase the capability of this processor. We'll have at least 2 more generations of this processor over the next 5 years. So from a raw performance point of view, this is going to be an incredible capability. And will make a huge impact on the way things are done in this space of high performance computing and solving these really tough problems for humankind.
From my perspective, the really crucial aspect here is that we've built a truly scalable technology, and this is what we've shown now with the 128 qubit processor. The integration of this programmable magnetic memory, the fact that integration hasn't caused an environment that is damaging to the quantum mechanics that's going on in the processor. We've been able to merge all of these different really challenging components to make this technology real, and to me that's why we can say it's truly a commercial quantum computer. In a lot of these other proposals for quantum computing, there's no they aren't truly scalable designs. There's no there's always a limit to how much it can be scaled up to before some other technology has to be invented or created in order to help that. With the design that we have now, it is a truly scalable design. In addition, it's incredibly performant. I mean, the way that we've designed this system you have the flexibility to run whatever types of problems you want. It's entirely programmable, and that I think is a very important element. We've tried very hard to make it as close and consistent with our normal experience with computers as possible, as opposed to being some exotic quantum computer and I have to be a PhD physicist to know how to even interact with this thing. It's actually something that's very simple that high school students can understand and could program and actually have. We've brought high school students through here to take a look at it. So I mean that's also a key thing. You could argue it's not a crucial thing because this is a quantum computer technology. That's not a crucial thing, but I actually think it is. That connection with the user is something that really makes this technology adoptable and applicable to the really hard problems that it will be able to solve. We've essentially removed or reduced those barriers as much as possible, and it's all those things to me that makes it a commercial quantum computer.
Imagine being able to predict patterns in weather so that you could prepare for really dangerous storms or earthquakes or maybe droughts. Imagine being able to predict patterns in the stock market so that you could detect if something was going wrong, like if there was an impending market crash. Imagine discovering patterns in genetic data that could lead to the advancement of new treatments for cancer or different treatments for diseases. All these tasks at the moment require an immense amount of computing and processing power, and what we have is we have computers that are just really inefficient at doing this, and we just throw more and more resources at these problems and we're still not managing to solve them very well. So what we're designing is a computing system that's much more efficient at solving these types of problems. It's really just a case of using the right tool for the job.
I was at UCLA studying physics. I've always been interested in the foundations of physics, the deepest aspects of nature. And obviously quantum mechanics is at the most foundational level. And I got recruited while at UCLA by a place called TRW. A professor, well, some people were interested in me. I did some work at UCLA as an undergraduate, published some papers as a junior college. And that got the attention of some people at TRW, and notably a kind of famous guy, Arnold Silver. He was the co-inventor of the SQUID, which is an acronym standing for Superconducting Quantum Interference Device. The SQUID's an interesting object because it's actually the basis of the quantum computer we're working on, and others in the superconducting community. And it's an object that was predicted historically to be the first object to demonstrate weird quantum phenomenon at macroscopic scales, something you can see with the naked eye. My first job out of college was with the co-inventor of the device, which would eventually be the device to show macroscopic quantum effects. And so when I got hired into this group, what the group was working on was quantum electronics, superconducting electronics. So that had the promise of operating much, much faster, 1,000 times faster, with 1,000 times less energy consumption, right? And this would be able to extend Moore's law well into the future and solve problems that would otherwise be beyond the pale of what CMOS could do, right? So that's what this group did. And so when I got hired, my initial attraction to that whole field was, one, they offered me a job. Two, I was working with some very well-known people who had done some brilliant work. And three, it was quantum mechanics on a tabletop. So we were building this technology, and we had the most advanced processing capability in the world at the time, and I learned a ton of stuff. I learned how to build superconducting electronics from the ground up. I learned all kinds of cool physics. And what I used to do for fun, I always, was trying to educate myself about new things going on in the field. Caltech had a series of free lectures, the Beckman lectures. And in 1997, I think it was, there was a lecture entitled Quantum Computing by a guy named John Preskill, a very a well-known and respected theoretical physicist. And I knew what quantum mechanics was, I knew what computing was, but I didn't know what they had to do with each other. It wasn't the buzzword that it is today. So I went to that lecture, and I took Arnold Silver, you know, the inventor of the squid, with me, and a couple other people from TRW, and we went to this lecture, and it blew my mind. You know, sort of this Alice in Wonderland stuff. I mean, one interpretation for quantum mechanics is that there's parallel universes, right? And that when you look at the quantum mechanical equations and they tell you that all these disparate physical phenomena are happening at the same time, you know, like the same physical object being in many places at once, or living out many possibilities simultaneously, that kind of thing. The idea is, you know, the basic idea behind quantum computing is if I can have single objects live out many possibilities simultaneously, what if I could have computing elements, the same physical hardware, behave as if it was many pieces of hardware, or one processor operating like it's an incredible number of processors operating in parallel, doing different parts of a very difficult problem. But the thing is, the way parallel processing is done today, you actually have to build physically new processors, right? But what if one processor could behave like 10 to the 500th processors operating in parallel? You know, it staggers the mind, right? So he was giving this talk, and David Deutsch, who was sort of the progenitor of quantum computing, he's a big fan of the many worlds interpretation of quantum mechanics. He came up with this idea by saying, you know, what if you could access all these parallel realities and do different parts of a complex computation in them simultaneously, and somehow extract information from the multiverse, right? This was an amazing thing. You're harnessing a whole new resource in nature. You're technologically accessing these parallel universes, and this is something that human beings have not been able to do, you know, heretofore. So I went to this lecture, had my mind blown, and at that moment decided that's what I'm going to do. And beyond that, I said, I'm already working with materials, superconductors, and building superconducting circuits and objects that behave quantum mechanically at a macroscopic scale. So when I walked out of that lecture, I thought, he's talking about doing quantum computing. He talked about, you know, doing it with ions, you know, nuclear magnetic resonance, photons. And when I walked out, I thought, well, yeah, those are all microscopic systems, and it's very difficult to access and control and manipulate and engineer microscopic systems. But superconducting circuits are macroscopic. If you could get, and they already demonstrate a lot of the requisite behavior, if you could build quantum computing elements out of superconducting circuits, you could have a macroscopic technology where it's already known how to build large-scale versions of that. So I got very excited about that idea. So I proposed it to Arnold. And at the time he said, you seem to really be into this. I liked it, your idea. I'll pay you 1 day a week to think about it. So 1 day out of a week, just and give me a lecture every couple of weeks about what you're thinking. So that's how that started. And in the course of that, over the next 2 years, I read every paper I could find on the internet, spending late nights at the UCLA library. And it was interesting because what I discovered was this amazing story that was going on. This idea, why is it if the microscopic world behaves in this Alice in Wonderland-like way, and we're made out of those atomic constituents, why don't we behave that way? Right? This was a big quandary. Why does quantum mechanics not work when you get to a certain scale? And yet we saw signatures of quantum mechanics in things like superconductors at large scales. So this is very intriguing. So when I started looking into this field, I found a paper at UCLA by a Nobel Prize winning physicist, Tony Leggett. And what he predicted in this paper was, if you wanted to see a Schrodinger's cat, now not actually a cat, but if you wanted to see a macroscopic object very, very large compared to the scale of atoms, that would be, you could put into two states simultaneously. He predicted it would be a squid. And that was, and I was working for the guy who invented it, and I was in a group where we built them routinely. I went to the UCLA library, I read that paper, and I went, wow. This was 1998 and 9, I was reading all these papers. So for 2 years, I read papers, I reported to Arnold Silver about my ideas about how to maybe pursue this field, about how we might leverage what was going on in superconducting electronics at TRW. And then I went in 2000, I went to a conference. It's called the ASC, the Applied Superconductivity Conference. And at that conference, there was a group in New York, SUNY, so State University of New York in Stony Brook. And a group, a guy, Jonathan Friedman and Jim Lukens, succeeded in making the world's first Schrodinger's cat. They put a squid in a macroscopic superposition of two mutually exclusive states, and it was in the New York Times. And I had been reading for 2 years, anticipating the day when someone would finally get to superposition. So they had tunneling, they had energy. And I went to that conference and I saw his poster, and I hadn't seen the New York Times yet. And it was like, my God, there it is. And what he had done, the simple way of explaining it is, if you take a ring of metal, it's just a ring of metal. You can look at it, the periodic table, niobium. You know, it's a pretty common material. But when you put that material at low temperature, in liquid helium kind of thing, it becomes a superconductor and has these macroscopic quantum properties. Well, what they had done is taking it to very low temperatures, millikelvin, and essentially put this in a very strange state of affairs. They had this ring of metal. There's a detail, something called a Josephson junction in there. But they ran a current clockwise, right? All the current was going clockwise. It's important. All the current's going clockwise. And all the current was going counterclockwise simultaneously. So they did an experiment that demonstrated this. So that's rather like you being at the velodrome on your bike and going clockwise and counterclockwise simultaneously, one individual, right? It's that kind of crazy. And I said, there it is. And so the New York Times article was Schrodinger's cat lives. So quantum mechanics does apply on the macroscopic scale. It's universal. And the reason we don't normally see it is because of all of these interactions with the external environment with this object. They had isolated the object sufficiently and it had the requisite properties to demonstrate the full-blown quantum mechanical effects at macroscopic scales. So this was, to me, a revolutionary thing. And I said, there it is. That's my quantum bit. Because there's lots of ways that you can represent zeros and ones. It could be the light switch, up and down. It could be a transistor on and off. And in this case, current going one way could be a 0. Current going the other way could be a 1. But you could put it in a state of being a 0 and 1 simultaneously. And that's a quantum bit. That's your qubit. And I said, that's the basis of the quantum computer I want to build. And I just hatched this idea. I thought, what if you could get some of the best researchers in the field, like the group that demonstrated this, get them well-funded, collaborate with a group like TRW that had this industrial might behind it to build devices, do experiments, microwave engineering, all that stuff, material science, because the materials, there's fluctuations in materials that make the quantum effects go away, but we had a whole material science division. So I said, what if we were to take that industrial might, kind of like when they ramped up the Manhattan Project with all the isotope separation, and then couple it with some of the best physicists in the field, and then beyond that, I said, you also have to look at applications. You have to look at the mathematics that underlies the quantum information processing. And those 2 years of reading, I had surveyed the entire field. I said, here are these physicists who are doing some great stuff. Here's TRW that has all this industrial might. Here's some guys who are doing really great algorithmic work. So I hatched this idea for a quantum computing Manhattan project. 2 weeks later to the day, a researcher at the Colorado branch of TRW
randomly called our group. DARPA has just issued a BAA, which stands for Broad Area Announcement, for where they are putting aside $100 million for projects in quantum computing. I said, I have this little mini Manhattan project. I'm going to figure out, I'm going to say how many people, what resources, how many experiments. I figured all that stuff out. I wrote milestones and all that. And I said, what would it take to do something substantive in 5 years? Minimum. And even then I was underestimating. And I came up with about $10 million, 5 years. And they said, you'll never win that. And I said, that's what I'm going to go for. So I wrote a very ambitious proposal. And in the meantime, I went and visited all these scientists who would be on the team and got to know their teams and the research they were doing, and put all the stuff in the proposal about what we would do, organized all the efforts so it would interleave in the right way with all the right stuff, and sent it in. And I thought, well, if nothing else, I got to meet all these really great, smart, interesting people, and been exposed to this field, and I know it's maybe improbable. Two months later, a letter arrived. You've been selected for your project. You won a $10 million DARPA project in quantum computing. And I was principal investigator. And that's how it started. So that was my DARPA project. Now, the DREAM project, very quickly, I came to realize that when working on government projects, tremendous bureaucracy, slow, working with academic groups that aren't used to working on a Manhattan project. They were disparate groups in different locations. They had teaching responsibilities. They had, that kind of thing. The culture wasn't the right kind of culture. I started realizing I need to co-locate these people. They have to be dedicated to this and this only. They have to be used to hitting milestones. And one of the first things that I knew wouldn't work is I said, well, okay, here's $10 million, put it in a bank account, and then based on the milestones that we've agreed to, I will pass out the money. What they did instead was they said, oh, here's how much money you had allocated to the SUNY group and this group and that group, and they were giving it to them individually, and I said, you just ruined the team, because while they'll be nice and collaborative with me, unless there's somebody who's handing out the money and there are deliverables and all of that, I could see the writing on the wall. I said, this is not going to happen. Well, I was giving one of these talks to the broader community. Some people, I pissed them off. They thought I was being critical. I thought there was great physics going on, but I said, this activity, the way it's organized, will never build a quantum computer. And shortly after that, I was reading the book on Craig Venter and how he mapped the human genome. So there's this big international project, right? It's going to take a decade and billions of dollars. And he said, I'll do it in 3 years for $300 million. And he did, right? And there's caveats there, but nevertheless, I looked at that same thing. And I said, that's another model of a more recent variety. And I was also directly involved with a friend of mine who left TRW, built a company, and built a microfluidics technology, so this microscopic, chemistry lab on a chip kind of thing. Problems that had existed for decades, he solved in months. And I saw how he did it, rapid prototyping, lots of experiments per unit time, kind of a similar philosophy to what I had. So I was at a conference, and I was giving a talk to this effect, here are my impressions about what we need to change to make this happen as a technology. One of the people in the audience was Colin Williams. He was a pretty prominent guy. He used to work with Stephen Hawking, in cosmology in Cambridge. Got very interested in artificial intelligence. Ended up being he was a professor at Stanford. He wrote the first textbook on quantum computing. The textbook that Geordie Rose read that got him interested in the field. Now at the time, Geordie Rose, who was doing this intellectual property company, he had a few people. The idea was, if somehow I could shuttle venture capital to groups that had promising sort of models for quantum computing or hardware implementations, because I'm a theoretical physicist and this group I'm working with understands that stuff, we can be this kind of the people between the resources and the people who are doing the research, the experimental research. So they said we would provide direction, technical direction, theoretical support, money, equipment, whatever, to and assess the various models of quantum computing, shuttle money and resources to the best groups doing what we think are the best ideas, in exchange for which we would get intellectual property. And then we build this big patent portfolio, and when quantum computing comes of age, and we have all this intellectual property, we clean up. That was the business model. That was the 1999 D-Wave that started up. And he was doing that for a number of years and came to the conclusion, the same conclusion I did for different reasons, that this disparate amalgam of researchers, distributed researchers, will never build a quantum computer. There's not enough cohesiveness, culture, drive, ambition, whatever. So he was getting frustrated. And this was I think he was about 5 years into the project. Yeah, because it was about 2004. I gave this lecture. I won my DARPA contract in 2001, worked on it for 3 years. Cool science, but I was dismayed at the pace of things and where it would go. I gave this talk. So Colin Williams, whose book I'd also read, approaches me after this lecture and says, we should start a company. Now, I said to Colin, no offense, you're a theoretical physicist, don't know how to start a business. I don't either. I think I know how to put together a good technical project and run it and inspire people and all that, but raising money and venture capital, I don't know anything about that. Now, we were sitting at Stanford late at night in a little cubby hole, overlooking some nice garden, and he said to me, well, there is this guy, Geordie Rose, in Canada. And he said, this guy raised $20 million. And that was the moment where I said, aha. That was my next aha moment. I said, doesn't it make more sense for us to team with the guy who's already raised the money? Because you think that my Manhattan project's the right way to proceed, and he has the money. And how about that? So eventually he thought, well, it'd be nice to own more of the company, but maybe that's a good idea. So he wrote a very nice letter of introduction to Geordie saying, if you want to build a quantum computer, you should talk to this Eric guy. I think he has the plan to do it. And vice versa, sent me a nice letter about Geordie, introduced us. And this was the difference I noticed with Geordie. Oftentimes you'll meet someone, have a conversation, they'll have action items. Oh, let's meet in a month and have lunch and discuss. So Geordie got that letter, and I got a call the next day. He was in France with this group in Saclay. They was actually doing some good work. And he said, I hear you have a plan to build a quantum computer. I said, yep. And he said, I'm in France. And I thought he would say, maybe we'll meet in a couple of weeks, or could you come to Vancouver? And he said, I'm going to buy a plane ticket. I'll see you tomorrow. I was at TRW, and Geordie showed up. I remember picking him up at the, he was at a little hotel by the airport, and we didn't know what each other looked like, but somehow I think Colin told him I was a rock climber, and he said something about Geordie being a wrestler in the Olympics or something. So I showed up in this little hotel, and I see a guy who didn't look like a physicist, this big bulking guy, and I said, the wrestler. He said, the climber. I took my mini Manhattan project proposal and said, this is what I would do. This is what I wanted to do in this government contract, but because of all this, disparate labs and conflicting cultures and all of that. And he said, here's my business model. What do you think of it? I said, it'll never work. And he asked me why. And I gave him a whole set of reasons. And he agreed with them all. He said, that's exactly been my experience the last 5 years. What would you do? So for 3 days, I told him what I would do. Who I would hire, how you hire a team. It has to be applications driven. Like, even though it was at an early stage, it's like, what are you going to do with it if you have it? You have to start thinking about it, because the applications define the architecture, define the device requirements, right? So I said, let's start from a processor, not from individual elements. What is this thing going to do? And then let's ask ourselves, is there a model that's easier to achieve. So I had this idea, like there's this continuum of quantum effects. Some are easier to achieve than others. Could we build some device that didn't have the full palette of quantum mechanical effects but still did something useful on path to the dream machine? You know, we had this evolutionary idea for quantum computing. And then, you know, after 3 days he said, let's make your vision into the new vision for D-Wave. This is phase 2. Let's go from an IP company to a technology development company. Let's do what you just told me. So I said, and he said, I got $20 million, hire your dream team, let's go. I never had anybody say that to me before. So it's like, wow. So I decided to take him up on it. I took a little time at first just doing kind of part-time, and then pulled the trigger and said, okay. Our first dilution refrigerator was something I bought on our Quist project and talked to DARPA and got them to transfer it to us. We paid for it, but so instead of 18 months, we were online in a month. Recommended a group of people, so there were a bunch of world experts, superconductivity circuit designers, and physicists from TRW who worked with me before, and I hired them. I hired some of the best people in the world from TRW. We hired a guy that he and I liked from Maryland, who had shown the first quantum entanglement in superconducting devices. And then I started hiring like the core technical team, and then he had the theoretical physicists that he had before, and we put the team together. The next big hurdle was, how are we going to build things? We need a superconducting fab. This brought up another issue. This is about doing things in a different way. The conventional wisdom for a long time in the superconducting community was that, well, you can't get like the semiconductor community guys to build superconducting, circuits. All of the superconducting groups in the world that built superconducting circuits were usually physicists, with some technicians or something. They would build their own clean room. They would buy a few pieces of equipment. The problem with that is it was never done in a production facility, and it was like, little wafers, one wafer at a time. And I looked at that when I was at TRW, because I did that too. I learned how to build superconducting circuits from the ground up at TRW, because I had to for my research. And I said, doesn't it make more sense to teach people who make 1 billion devices on a chip how to do superconducting stuff? It's not exotic to build. The physics is exotic at low temperature, but it's not that exotic to build. So very long story short, myself and Jeremy Hilton, who you've met, the VP, we searched the world for a semiconductor world-class kind of environment, like an Intel environment, that was willing to do R&D, smaller volumes and different materials, and landed here at this facility. And I taught semiconductor guys all about superconducting stuff. I didn't hire superconducting people, I hired semiconducting people, and some best in class who were responsible for 65 nanometer technology, and that became the D-Wave team. I put a deal together with this place in Silicon Valley and leveraged the capability here, and in 2.5 to 3 years, we bypassed the world capability in superconducting circuits that had been building for 40 years. And I said, this is the Craig Venter Manhattan Project. It's like, because we had to, because you can exist in these other groups that get government funded over the years. They never get past a certain place, but it's okay. You keep getting this government money. In our case, if we couldn't build a process that exceeded everything in the world in a couple of years, we were out of business. So we did. So we had to get creative. So came to Silicon Valley, taught semiconductor people how to do superconducting stuff, and we bypassed all the capability in the world in a couple of years. So, and that kind of brings us to where we are today. We have, and in the interim, we have 70 people in Vancouver, a team at JPL, which still does R&D and material science for us. world-class superconducting group here, and in the meantime raised $80 or $90 million, right, which was bigger than the entire U.S. budget for the. So it's like it worked out.
Some of the technical things that you have to overcome as a builder of one of these machines requires that you build parts of your computer in ways that are entirely novel. No one's ever done them before. So one, if you're going to build a quantum computer, it has to be really cold. And the temperatures that you have to achieve are some of the coldest temperatures that we know of in the entire universe. And in fact, the temperatures that we achieve in our computers when they're operating are several hundred times lower than the temperature of interstellar space. And they're achieving temperatures that have there's nothing in the natural world that gets you down to temperatures like this. If there are no other intelligent life forms in the universe, these are the coldest places in the universe. When we operate the D-Wave 1 computer, the temperature of the chips is likely among or the coldest point in the entire universe. There are other very difficult technical problems that we've had to solve along the way. One of them is a problem which is how do you program a quantum computer without disrupting its behavior? So quantum computers have this strange, seemingly paradoxical set of requirements that, on the one hand, you as your large, hot blob of a lot of mass, highly classical fingers, have to somehow tell this thing that lives down in the very cold and the very quiet what you want it to do. And you have to be able to change what you want it to do from run to run. You don't always say it's solving the same problem. It has to be programmable. So how do you convert these into that? And that is an unsolved problem for every quantum computer architecture except D-Waves. We've solved that problem. We've solved it in a way which is scalable to as large a computer as you can imagine building of this sort. That was one of the biggest marvels of engineering brilliance and creativity that I've ever witnessed. The team that did this comprises the best circuit designers combined with the best physicists available for this type of work, and they worked on this problem for many years before coming up with this brilliant solution. It's creative, it's exceedingly simple, as all good engineering designs are, but it solved a problem. And what's even more spectacular is that the very first time we tried this idea at scale, it worked. And that, given the complexity of this type of system, is an astounding fact.
What ended up happening, how the course of the project went through, we actually took the entire first month just establishing what the requirements of the project were, and really understanding that we were building what we needed to build, that we understood what our requirements were, and that we were going through with a design that was going to meet those. It took a tremendous amount of work and coordination on everyone's part. The group grew from about 5 people to about 12 people by the end of the project. New people were coming on board. We were talking about the constraints of the design. Everyone was trying to help out in whatever way that they could in order to accelerate the progress. And finally, at the end of the project, the whole system came together. We installed it on a refrigerator, and I watched 2 of my friends and colleagues basically put the system in and begin its operation. That was part of a project. Then it gets handed off to the testing analysis. That's when they can begin testing chips. And we had some goals and deadlines for when we needed to get operating chips completed by. And they then carried the torch and worked lots of overtime and ran through problems. And they were able to achieve the goal that they needed by the subscribe time with 6 hours to spare. So when you think about the project as a whole. If you actually build it and then you begin to test it and it's not working, you have to go through another design iteration, you're sunk. So every generation along that line has basically had to work the first time completely. That wasn't sort of a magical process. We basically, the approach I took at the time was to just do a lot of rigorous testing during the build. Basically check and recheck and dip, do thermal cycles and dip things in cryogens and see if they would break as you were going along. Because once the system was built together, you can't take it apart. You basically start from scratch again. So we did a lot of rigorous testing during the build phase, and then when we came together, we crossed our fingers and held our breath, and the system worked.
The opportunity to do something that was unique, that was new, and it wasn't just quantum computing. It was actually quantum computing at D-Wave that really attracted me, because it was an opportunity to do something with a group of people that were really obviously serious about trying to build something and trying to sell something, and so I think that's what that aspect of it fascinated me as much as the fact that it was quantum computing. Quantum computing is an amazing idea, and it's not one idea. It's actually sort of a broad collection of ideas, but it's trying to harness aspects of quantum mechanics to do computation in a way that hasn't been done before. At least this is sort of a very broad way of defining it. The people that this problem has attracted, that are just, they're some of the most interesting and intelligent people that I've interacted with, and it's just a pleasure to work with all these people. So I mean, that's the other thing that makes it really a great sort of enterprise to be involved with.